Hello everyone. So in this lecture we will continue to talk about the infinite limits and vertical asymptotes. We had already started limit topics at the previous lecture, and we have already processed the first 11 slides in this presentation, and we will continue with the vertical asymptotes. So we have a rfx function which is 1 over x minus 2. So this function, first, we let's talk about the fx equals x square function, for example. When limit x goes to infinity, we know that this function is going to infinity because we have x square. When you replace x with the infinity, you are going to infinity. This part, this function is satisfying this infinite limit parts, because when x goes to infinity, your function is going to infinity, which is the infinite limits parts. But this function does not satisfy vertical asymptotes parts, or this function x to the cube or x square plus 5, etc. They are all going to infinity when x goes to infinity, but we don't have vertical asymptotes for those kind of functions. Why? Because your x value is not going to a certain constant. It is going to it is growing to infinity or minus infinity. It could have been case that this is going to minus infinity, and in this case it is going to infinity, and in this case it is going to minus infinity. So, since they are not approaching to a certain constant value, for those kind of functions, we cannot talk about vertical asymptotes. We can talk about this vertical asymptotes only when the function y value goes to infinity or minus infinity, when x values are going to getting closer and closer to a certain constant. For example, we have two constant here. Two is a special case here, and which is our vertical asymptote. Then let's calculate the limit of that function when the x goes to 2 from plus side, from the right side, 1 over x minus 2. For this function, you cannot just put 2 as a parameter, because it makes the derivative 0, which makes the function undefined. That is why we are taking the limit of that function from the right side. When you approach to x values from the right side, that means you are using the values that are greater than 2. For example, you are using a value 2.000000001. So when you remove 2 from this value, you will end up with very small positive number in denominator. And when you convert that one, you will end up with very big positive number, which is plus infinity, which is like plus infinity. When you approach to when you make this number closer and closer to. So this is the behavior. You are approaching to from right side. This is right side. You are using values that are greater than 2, and your function is going to plus infinity. When you approach from x from the left side, that means you are using the values smaller than 2. You are using a value something like 1.9999999, etc. And minus 2, you will end up with very small negative number here. So when you convert that very small negative number, you will end up with very big negative number, and that means it is going to minus infinity. So you have 2, and you are approaching 2 from the left side. You are using values smaller than 2. You are approaching from the left side, and your function is going to minus infinity, because you will end up with a very small negative number in denominator. And when you convert that number, you will end up with something like minus 0.000000001 1 over. So we will have, for example, minus here. This is very small positive number converted very big positive number, and times minus 1, you will end up with very small negative number, which is going to minus infinity. So this is vertical asymptote. This is the behavior of vertical asymptote. The x value, you are approaching a certain x constant, and the function is going to plus or minus infinity. That means you cannot give that 2x value as an input parameter, because that makes the function undefined. But when you approach it, your y values are going to infinity or minus infinity, and it becomes vertical asymptote. So next we will talking about infinite and horizontal asymptotes. But before talking about those, I would like to explain this function, some clear-cut shortcut functions, shortcut rules, so that we can simplify our limits and calculate them easily. For example, when x goes to infinity, you had if you had a function like x squared plus 5x plus 2, let's say 3x squared divided by 8x squared plus 4x. So you have two polynomial functions, and you are dividing them, and when x goes to infinity, in this case, what is the greatest term? What is the term with greatest exponential in the numerator? It is this 3x square term. And what is the coefficient of it? It is 3. What is the term with the greatest exponential in the denominator? It is 8x square. This is also a term, but it does not have a greatest exponential. This has the greatest exponential, which is 2, and its coefficient it's 8. So in this case, you can think of this as both numerator and denominator is growing like equally. They are growing equally because they both have the same exponential. So we can just use the coefficients of those terms in order to calculate the limit, and it becomes 3 over 8 in this case. So this is one shortcut rule to calculate the limits. For when x goes to again infinity, if you had a function such as 5x to the 8 plus 7x 7 divided by x squared plus 2. So in this case, for example, you have a function in numerator whose greatest exponential is 8, and the coefficient for that exponential value is 5, and for this one greatest exponential is 2, and coefficient is 1. But since 8 is greater than 2, we can just say that numerator is growing quicker compared to denominator. Since numerator is growing quicker, we can just write it as going to plus infinity, because they don't have the same exponential value here. In this case, they don't have the same exponential value. So checking or taking the ratio of coefficients is not possible in this case. It is only possible when you have a numerator and denominator having the same exponential, same greatest exponential value. In this case, you can just take the ratio of those two coefficients, numerator coefficient and denominator coefficient. So in the third case, we have again limit x goes to infinity. This time we have something like 2 to the x 5 plus 4x plus 2, uh, 2 divided by uh, x x to the 8 plus 7 x to the 5, for example. In this case, we have again we don't have a same exponential in numerator and denominator. This time is denominator is growing quicker compared to numerator, because we have x to the 8 here, x to the 5 here as the greatest exponential. So this is growing quicker compared to this. So that's why the coefficients of those two terms are, they are not important. We cannot use those coefficients, and we can just say this is going to 0 because denominator is growing quicker. So those are the rules explaining this. When denominator is denominator of when the degree of numerator is smaller than degree of denominator, which is this is the third case I just described, and degree of numerator is smaller than denominator, and degree of degrees are cubed, which is the first case, which first example I give, and this is the second example. Degree of numerator is greater than degree of denominator. This is the second example I give. So those are the shortcut tools. When we talk about horizontal asymptotes, we have when x goes to a certain plus infinity or minus infinity, whether your function is going to a certain value. So that's why it's called limits at infinity. Your function, not your function, your x value is going to infinity or minus infinity, and you are checking whether your function y values are approaching to certain constant. It is just like the reverse of this. Here you are in for the x value you are approaching to a certain constant and you are checking whether y values are going to infinity or minus infinity. Here on the other hand, your x values are approaching to plus infinity or minus infinity, not to a constant but plus infinity or minus infinity, and you are checking if y values are approaching to a certain constant value. So we have, in this case, we have a horizontal asymptote, for example, for this function, 3 to the x plus 1 divided by x plus 5. So when x goes to infinity, again here, when x goes to infinity, since their exponentials are same, the exponentials are the same, we can just use the ratio of those two coefficients, ratio 3, and we will end up with 3. So we will have we will have a horizontal asymptote, which is like y equals 3 xy. And for this one, our function is getting closer and closer to 2. And at which point our function is crossing the x-axis, we need to solve this function. So we have fx function equals 3x plus 1 divided by x plus 5. So in order to cross with x function, x axis y equals 0 axis. So y must be, this is y must be 0. Uh, 0 equals 3x plus 1 divided by x plus 5. So we must have minus 1 over 3 here, so that this becomes 0 and this becomes a certain value which is 0. So x is minus 1 over 3. So our function is crossing with the x-axis here, minus 1 over 3, and it is approaching it to 3, and we can just say that our function is like this. This is an hyperbola, not parabola, hyperbola. It is crossing x with the minus 1 over 3, and it is approaching the 3. It never touched the 3. Uh, and this since this is an hyperbola, we have also second part of this graph, second part of this function. We have already calculated the horizontal asymptote. What is the vertical asymptote? We have already learned how to learn vertical asymptote. Here, this is also a hyperbola. We have x minus 2. We cannot give 2 as an input parameter. Here, we cannot give minus 5 as an input parameter. Why? This makes the denominator 0, and which makes the function undefined. So that is why we have the rest of the function minus 5 being the vertical asymptote, minus 5 being the vertical asymptote, and your function is getting closer and closer to this minus 5 value, and never touches the minus 5. And when you are approaching minus 5 value from this right direction, you are giving a value something like minus 4.999999 for this value, and you will end up with very small positive number here. You have negative number here because you have given minus 4.999 as an input parameter. This is negative. This is very small positive number. You will end up with, when you convert this again very small positive number, you have very big positive number. When you multiply it with minus value, you will end up with very small negative number, which is minus infinity. And this is how it behaves in the second part. You have, when you approach this minus 5 from this direction, from the left side, you are giving something like minus 5.00000001 as an input parameter when you approach from this direction. So that's why when you give this as an input parameter, you will end up with here a very small negative number, and here since you used a negative number, minus 5.0001, this is also negative. You have a very small negative number here. Negative negative will become positive, and that's why your function is going to infinity. You had a very small positive number at the end, because two minus cancel each other. A very small positive number here. When you convert again with the numerator, your function is going to plus infinity. And when x goes to minus infinity, this time when x goes to infinity, it is 3. When x goes to minus infinity, here in this direction we are going to minus infinity, x goes to minus infinity. This is again 3, this is approaching again 3, because minus infinity here, minus minus will cancel each other, plus you have 3. So that is the behavior of that function. If a function is continuous, if and only if you have a limit of that function, assume that you have when limit x goes to a certain a value, for example, fa, you must have this limit value, which is which is, let's say, equal to b, and you must have an fa value which is equal to b. In only if those two are true, you can then say that the function f x is continuous at b, at a, sorry, at a. So you must have a function whose limit exists and whose limit must be equal to a, must be equal to b, and you must have the same function whose value is b when you give x equals a as an input parameter, and value of the function at that point must be equal to limit of that function at that point. So when they are equal, you can say the function is continuous. When they are not equal, you have discontinuity, and we have three different types of discontinuities here. Removable discontinuity, jump discontinuity, because you have a jump here. From here to here, there is a jump, because that's why it's called jump discontinuity. And infinite discontinuity, because the values, y values are going to infinity, or minus infinity. That's why you have an infinite discontinuity, and this is a vertical asymptote, vertical to x-axis. That's why it's called vertical asymptote, as we have processed in two previous slides. So, for example, we have a removable discontinuity. We have this function. It's like it is just behaving like a line apart from this 2 point. So this is probably 0, 1, 2, 3, and 2. It will have a point. It will cross the x axis with the point -2 probably, and you will have a function. I remember this function from our previous slides. Fx equals uh, this is a point 2 to 4. Fx equals x squared minus 4 divided by x minus 2. So this function, you can simplify this one as x minus 2, x plus 2. So for this function, you can simplify it and you can just write x plus 2 as the function behavior, but apart from 1.2, because you cannot give 2 as an input parameter, because which makes the function undefined. So that's why we have an empty circle here. We are not able to give 2 as an input parameter. But apart from 2, when you don't consider 2 as an input parameter, it is just like behaving x plus 2 line. Why? Because when you give 0, it is its y value is 2. When you give -2 as an x, as an input parameter x, it is crossing with the x-axis, which is y equals 0 axis with -2. So this function is behaving just like x plus 2 apart from 2. And we have removable discontinuity here. Why it's called removable? Probably because when you remove this point, it is just behaving like a line which is continuous. That's why it's removable discontinuity. But I am not sure. So, so this is a piecewise function. We can write this function as a piecewise function. For the values smaller than 0, it is just behaving like x plus 2. For the values that are greater than or equal to 0, we cannot give 0 as an input parameter here because it is undefined. It does not have in the domain of this line. It has the 0 value. 0 has in the domain of this line, in the domain of this part of the function. That's why we should write x greater than equal to 0 here. So we have x plus 2 here. When you give -2 as an input parameter, it becomes 0. When you cannot give 0, but if you were to give 0, it is crossing with the y-axis with the 2. So this is true. So and we have this line, and this line, when you look at this, those lines have the same slope, and this line, orange line, is crossing x-axis with the -4 point, and the blue line is crossing x-axis with the -2 point. So this orange line is just the moved version of this blue line. It is moved to plus y direction by 2 point by 2. So we can just write it as x plus 4. So when you give 0 as an input parameter, it is 4 here. When you give minus 4 as an input parameter, it is 0. It is crossing with the x-axis 0. So this orange line is x plus 4. We have those piecewise function. So we have a jump here. That's why it is called jump discontinuity. Function is continuous here, and here discontinuity exists. And there is a jump, so it continues, and it continues to be continuous after that point. So and here at the end we have infinite discontinuity. I remember this graph, and this is just fx equals 1 over x hyperbola. When x goes to infinity, this function is going to 0. Limit x goes to infinity. Sorry, let's write here limit x goes to infinity 1 over x. X goes to infinity 1 over infinity 0. Limit when x goes to minus infinity 1 over x. Their values are again the denominator becomes minus infinity, and the y value is going again 0. When x goes to 0 from right direction, we need to check right and left direction, and limit when x goes to 0 from plus, and when limit x goes to 0 from minus direction. So from plus direction, from here, from right side, our values are this. We will end up with very small positive number here. When you convert again it, you will end up with very big positive number, which is plus infinity. Here you will end up with very small negative number, very big negative number. Actually, you will end up with something like minus 0.00000001, etc. And when you convert it, you will end up with a very small negative number, which is minus infinity, here. So we are assuming that this function is continuous. If this function is continuous, we need to find the k value. Assume that function is continuous. What does it mean for a function to be continuous? Function must have a limit value. We have piecewise function for values greater than smaller than 2. It is behaving like x squared plus 1. For values greater than 2, it's behaving like kx minus 1. So we have a special value 2, and when you consider this to be continuous, when limit x goes to 2, from right side or left side, when limit x goes to fx must exist, and must be equal to f2. For this limit value to be exist, for when x goes to fx, in order for this limit to be exist, right side of the limit and left side of the limit must exist. Fx must be equal to, and must exist and must be equal to each other, so that we can say the limit exists. Fx. So when you approach x from right direction, from using great values, this is right side limit, left side limit. They must exist and they must be equal to each other. So uh, here, when we use these x values to get that are greater than 2, this is simply right-sided limit, because we are using 2 plus, which are values greater than 2 or equal to 2. This is simply kx minus 1. And for the values that are smaller than 2, we are approaching the x from the left side. So it is simply value smaller than 2 and x squared plus 1. So here, and this is a kx minus 1, this is x squared plus 1. Since they are polynomials, here we have a line, here we have polynomial. You can just use substitution rule to solve this equation. We have 2 here, 2 here. We just need to replace with x with 2. 2k minus 1 equals 5. So you will end up with k equals 3, which is the coefficient for this one. And you will and f2 must be equal to those limits. We have already calculated that the limit for those is 5. F2 must be equal to 5 also. When you give 2 as an input parameter, 2x is greater than or equal to 2, we must use this formula. So 2 times 3 minus 1 equals 5. F2, which is 5, which is equal to limit from right side and limit from left side, which is equal to limit itself. So we had fundamental trigonometric function formula for when limit x goes to 0, sinus x divided by x equals 1. We need to memorize this as our rule so that we can solve the next questions related to this rule. So we have, for example, here another question related to this rule. We have when limit x goes to 0, sinus x 5x divided by x. We need to make this formula. We need to make this function similar to this so that we can solve this problem. How can you make this function similar to this? We have x and x here. We have 5x here, so you must have 5x here also, so that we can solve this problem. So we have put already 5 here, so we must put for the numerator, we must put 5 here also. So limit x goes to 0, 5 times sine 5x divided by 5x. You can just put 5 outside according to constant rule in the limit. You can just put 5 outside as the limit. 5 sinus 5x divided by 5x. This is similar to this when x goes to 0, sin x divided by x 1. When x goes to 0, sin 5x divided by 5x. This is also going to 1. So you will end up with 5. Here, limit x goes to 0, sine 7 and x divided by sine 2x. We have those two sine functions, and you need to make it again similar to this one. So we must have limit x goes to 0, 5x sine 5x divided by 7x sine 7x divided by 7x divided by 2x sine 2x divided by 2x. So we have 7x and 2x here. According to product rule in limit, we can just write this as limit x goes to 0 sine 7x divided by 2x times limit x goes to 0 sine 7x divided by 7x, and we can, according to coefficient of the limit, we can rewrite this as limit x goes to 0 sine 2x divided by 2x. So sine 7x, think of this 7x as u parameter. You have limit x goes to 0 sine u divided by u, or limit x goes to 0 sine 7x divided by 7x. This is similar to this. So this is becoming 1. Here also limit x goes to 0 sine 2x divided by 2x. This is also becoming 1. So, and at the end we have limit x goes to 0, 7x divided by 2x. X's are simplified. You will end up with 7 over 2 as an answer to this question, 7 over 2. So there is a useful tip here also, limit. This is also x goes to 0. Limit x goes to 0 tangent x divided by x, which can be rewritten as sine x divided by x times 1 over x. This is 1 over cosine x. So, and according to, again, the product rule, you can rewrite this as limit x goes to 0 sine x divided by x times limit x goes to 0 1 over cosine x. This is just like this formula. This is 1. Limit x goes to 0, 1 over cosine x, 1 over, you can just use substitution here. Cosine 0, what is cosine 0? When angle is 0 in the unit circle, cosine 0 is equal to just radius for that unit circle, which is 1. So that's why limit 1 over 1, 1. You have 1 here also, 1. You will end up with 1 here is an answer.